Okay, welcome everyone for the part 2 of Olas Dev Kickstart. We're really happy that you were all here today, and we are gonna follow the content for the Mech tools. And I'm gonna give the word for David V. Thank you, David, for presenting.
Hey, Caroline, thank you for having me. So let's start with the part 2 of Olas Dev Kickstart 2. But as always, and before we start, let me read the usual disclaimer. This session is organized by Valerie in order to educate people about Olas and developing autonomous services. Valerie is one of the core contributors to the Olas ecosystem, and all the content we provide here is an expression of our view and therefore does not constitute financial advice. With the disclaimer out of the way, let's go for it. So today we are going to follow a similar structure to what we did yesterday. First, we will present ourselves so people that are watching us on YouTube are aware. Then I'll go with a small recap on what we learned yesterday, and then we will start right away with the second session, lab session, about building our own Mech tool, where we will learn how to build our Mech tools, and we also will have a question and answer session at the end. So yeah, let's go with the presentations as usual. Carol?
Yeah. Yes, so I'm Carol, product manager here in Valerie. My role is to take care of the developer experience, the Dev Academy, and how we can make it easier for developers like you to learn the Olas stack. Being in crypto for 3 years now, mostly in community, dev relations, and marketing. And before that, I've worked in big tech companies like Facebook and Google, and I'm also a qualified lawyer. Thank you, David.
All right. And myself, I'm David B., senior software engineer and founding member of Olas. I have a PhD on mechanical engineer, but nowadays I work as a software engineer. And I guess in the call we also have Jose. Do you want to introduce yourself, Jose?
Yes, thank you, David. So I think I don't have a slide, but I can introduce. So I'm also a software engineer at Valerie. I'm a founding member of the Olas DAO, and my background is on security, cryptography, and so on. And I will be around in case I can provide some help during this Kickstart Academy.
All right. So before we start with the material for today, let's do a quick recap on what we talked about yesterday. So yesterday we presented a bit about what's the goal of this Dev Kickstart course. Then we made a small and quick intro to Olas. We were talking about autonomous agents, how we build them, what they can do, and then we focused on explaining what Mech is and what the Mech tools are. And we had this lab session number 1, where we sent a Mech request using the Mech client. And today, we are going to build our own Mech tool, and we will be able to test it locally. And we will also learn how we can integrate it with the Mech agent. And before that, let me show you once again. I think we had a quick glance yesterday at the Mech repository, but let me once again go there and show you what the Mech repository looks like. So almost all the repositories of any agent services implemented by Valerie look like this. Like you have some folders, some files, and the important part here is the packages folder that includes all the packages implemented by all the developers that contribute somehow to this specific service. In this case, whenever we go into the packages folder, we can see several names. We have Gnosis, we have Naft AI, we have Polywrap, we have Valory. These are all the contributors that have coded some packages for the Mech service. I am going to go inside Valory, and inside each of one of these folders, there are different package types. We have agents, we have connections, we have contracts, customs, protocols, services, or skills. Sometimes there are a lot of them, sometimes we only will find one, but today we are focusing on just learning about Mech tools. And Mech tools are always located inside the customs folder. So I'm going to go into the customs folder. So we are now seeing the Mech tools that have been implemented by Valory. These different tools do different things. Some of them call ChatGPT, some of them call other LLMs, some of them prepare transactions even. You know, most of our tools are focused on AI tooling, but that's not a requirement. I mean, you can have a very simple tool that just does some stupid thing or very simple thing, or that uses, I don't know, a Twitter library to retrieve some tweets. I mean, there's no restriction on which kind of things you can do inside a tool, although most people focuses on implementing AI-related tools because that's the most interesting thing nowadays for agents to offload. So whenever we go into one of the tools, for example, let me go into OpenAI request, one of the most popular one, we find, let me know if the font size is too small for your screen. Each of these tools contains at least 3 different files: init.py, component.yaml, and OpenAI, in this case, OpenAI underscore request.py. This name will vary depending on the tool. So let's go one by one and understanding what each of these files are. Starting with init.py, which is basically can be an empty file. This is the traditional module file for Python modules. Basically, you don't need to include anything here. We usually include the copyright header and just a small bunch of text here explaining what this module is for. But you can have just an empty file here. Then we have the component.yaml, which is a configuration file that only contains a bunch of metadata related with this tool. For example, it contains the name of the tool, the author who coded this tool, the version number for this tool, 0.1.0 in this case, the type, in this case, in the case of Mech tools, it will be always custom. If this was a connection, it would be set as connection, but yeah. For all of you who will be coding a Mech tool, you will set this as custom. Then we have a short description, the license. AEA version is the version of the AEA framework that we will be using. You don't need to touch this for now. You can basically copy paste almost everything and just change the relevant parts to you. And then there's a fingerprint. Basically, these are the hashes of the 2 other files. These hashes are automatically calculated. We will see how to do that at the end of today's lesson. And the same goes for the fingerprint. Ignore patterns. You don't need to take care of that. The entry point contains the name of the file that implements the tool. In our case, this is OpenAI request.py. So this is what we set it. This is the file that the Mech will load in search for the tool. Then there's the callable, which is the name of the function that will be run. So these 2 pieces of information let the Mech know which file needs to load and which function needs to call. So in this case, the Mech will load OpenAI underscore request.py and will search for a function called run, and that's the function it will call. And then Some tools might have some dependencies, some tools might have not. In this case, the OpenAI request uses the OpenAI library, so a dependency can be set as this. You set here the name of the library, and then you specify the version that you need for this library. Here, we can see that there's two different dependencies on this tool, and that's it for the component.yaml. Basically, whenever you implement a tool, you can copy paste from any other tool and just modify the name, the author, maybe the version if you're interested, maybe not, and then the description. I think for the rest, you can just leave it as is. And then, of course, there's the most important file here, which is the actual tool, which is implemented inside the Python file. So the most important thing you need to know about these files is that you need to implement one. Yes, we will. There's a question about if we will be using pip, maybe. You can use pip, we use poetry. I will be using poetry today, but yeah, you can basically you use either in pip, ppm, poetry, no problem. So I was saying that basically the most important thing that you need to know when you are implementing your own tool is that you need to follow the signature of this function. You remember how in the component.yaml we said that the function that the Mech needs to run is called run. The callable is set to run. So we need to implement a function called run, and this function needs to be exactly the same as what you are seeing in the screen now, because that's what the Mech will be expecting. This is a function that is expecting some keyword arguments. Those keyword arguments will be set by the Mech. You will do some actions. You will make some processing here, make some calls, whatever your tool does, and then the tool needs to always return 4 different pieces of information. The first one is basically the result of the tool execution, and the other 3, we will see them in a second, but are optional and can be set to null. I think the best way to learn this is by example. So let me bring up my VS Code here. And well, actually, let me show you another thing. This is the repository that we will be using today. This is the repo that we will be cloning, and we will be working on top of it. This repo contains basically a short explanation of what is a Mech. This is something that we talked about yesterday. Why do we need Mechs? This is the diagram I showed you yesterday that depicts how the Mech request response flow looks like. And then what I was saying, basically, what a Mech tool looks like. So this is what I just explained, right? The run function expects some keyword arguments and returns 4 different things. The response that now needs to be sent back to the user, and then 3 optional fields. One can be the prompt. If this is a LLM related task or tool, the prompt can be sent back. And then there's another couple of fields or objects that won't be covered today, but you just need to know that this is some transaction. I mean, some tools can create some transactions. We won't be doing that today. And other tools need to calculate some costs. So basically, we will be setting these 3 to none, but it's important that you know that you need to return this. The requirements that you need to be installed in your system is Python at least 3.10, pip, and poetry. Here you have the links to the installers, so you can install it in your system. And then I think we can start already. So first of all, let me copy. I'm going to clone this repository. It's advised that you do this at the same time as me. If not, or if this is too fast for you, then Don't worry, you will have time to do it later today, but it's important that you do this before tomorrow's call. But yeah, I encourage you all to basically follow me with all the commands I'm going to run now. And yeah, I think let's start by cloning the repository. So let me make this a little bit bigger. So I'm going to go into my temporary directory. Please let me know if this is too small or something. I'm going to git clone the repo. You can do this as well, downloading the zip file from GitHub, but I prefer to do it using Git. I am now going into the repository. I am going to prepare the virtual environment. This repository already includes the definition of all the dependencies, so it's enough if I just enter the virtual environment with Poetry shell and then install all the dependencies doing Poetry install. This will install all the dependencies that need to be installed, and we are now in the position of running some examples. So it's important to notice that yesterday we made a call to a tool that is deployed already to the Mech, so the Mech already integrated that tool. But today we will be focusing on first developing our own tools and testing them locally. We are going to see two different tools, one simple tool that will implement a calculator, and then we will continue with a more interesting tool where we will implement basically a prediction tool. If I open the repository, you will see that there's already, similarly to the Mech repo that I show you, there's a packages folder. Inside Valory customs, there's two different tools, calculator request and prediction request. So what I'm going to do is I am going to open calculator request.py and component.yaml. And you see that the component.yaml is almost the same as the one that we saw for the OpenAI request on the Mech repository. I just changed the name to calculator request, and then I updated the description. This tool does not have any dependencies, so my dependency is the empty set. And I also changed the entry point to calculator request.py because that's the name of the file where I will be implementing the tool. That's for the component.yaml. You can basically copy paste it. But for the calculator request, I'm going to delete everything here, and I will start coding from scratch. So the only thing I will be keeping is the definition of the run function. Once again, remember, it's very important that your run function always expects some quarks and nothing else, and returns 4 different parameters. One string, which is the result of the tool execution, and then we will return 3 different known values. So first, we have here some syntax problems because we are using some types that have not been imported. So I'm going to import from the typing module. I'm going to import the tuple, optional, dict, and any. Now we have function, and at least the minimum thing that we need to do is to ensure that we are following the function signature. So we now have a function that returns an empty string and 3 known values. This is the minimum amount of code to have an acceptable tool for the Mech. So as I was saying before, this will be a calculator tool that will let us add and multiply numbers. So let's start adding an add function. Let's do this. And let's define an add function that takes a first number and then a second number and returns first number plus second number. This is a very simple function. Let's add some documentation here. And we now can call this function. But first, we need to extract some values because which are the first and second numbers we're going to pass. So we are expecting the user to call this function and send some numbers here in the quarks. So I first need to extract these numbers from the quarks. So I'm going to go like quarks.get, and here I'm going to get something called. You remember that quarks is a structure similar to a dictionary. So I can do this, and I will do the same for the second number. Now I have the first number extracted from the quarks and the first number as well. So I am now in the position to call my add function and pass it the first number and the second number. Now we have a result, which should be a number, and we can return it already to the user. But remember, we always need to return a string. So we are going to turn the result into a string. This now should work. And to test it locally, I have prepared a script for you all, which is inside the scripts folder, run calculator request. So I am going to open this. You can see that basically what I am doing in this script, I am just importing the run function from the calculator request module. And I am just calling it. Let's forget about this for a second. I am just passing first number equals 17, second number equals 5, and then I will just print the result of calling this run. So remember, we are not making yet a call to the Mech. This is local testing, and I encourage you to always test your tools locally before trying to integrate everything into the Mech. So now I am going to run this script, running Python scripts run calculator request. I run this, and here we go. We have called the run function from the calculator request module, and we have this tuple as a result, which includes the number 22, which corresponds to adding 17 plus 5. Remember, this is a string. That's why it's being quoted. And then we have the 3 known values at the end. This is the simplest example we can think of now, but we are going to make things a little bit more interesting now. So let's say, all right, this is just adding calculator, but I also want this calculator to be able to multiply. So I am going to add another function, which is called multiply. We can improve the documentation here. And now instead of adding, we are multiplying. But now we have 2 different functions, add and multiply. And somehow the user needs to select which one he or she wants to run. So a small trick for this is we are going to create a mapping called available tools that includes the add key mapped to the add function and the multiply key to the multiply function. Now, I would like the user to not only pass the first number and second number on the quarks, but I would like also to get the tool name, which is basically the same thing. So quarks.get, and we get the tool name here. Now that I have the tool name here, I can get the tool from the mapping doing this. We access the mapping with the tool name. So we now get the tool. When we do this, basically, here we will have either the add function or the multiply function. So now instead of calling add, I will call the tool. And let's try once again. But let's make a small modification to our script. Now, the user also needs to pass the tool, all right? So let's call this script again, and we have an issue. Why? Because we have not, so tool name, yeah, this is expected to be tool name, and here the user is sending a tool. So let's update this and run again, and we get the same result again. But now we can do this. We can change the tool name from add to multiply, and when we run the same script, now we get a different result, which is a result of multiplying 17 by 5. But if you have been paying attention, you can see that if the user somehow messes up the parameter names or sends, let's say, for example, what if the user forgets to add the tool name? Now, we will get an error, right? And the tool will fail. So it's the responsibility to handle these cases as well. So there's a lot of things that can be wrong. Users can forget parameters or can misname parameters. So it's our responsibility to check that all the data that is needed for this tool is in place. So I'm going to add another function now for handling errors. And this will be called error response. It will receive a message, which will be a string, and will return basically the message and 3 known values. So what will happen is whenever we find an error, we will call this, and the user will receive the error message and 3 knowns. So let's start, for example, thinking what can be wrong with the first number. So, for example, the user could forget about setting the first number. So we are going to add here a default value. And now, if the user forgets to set the first number will be set to none. And we can do the check, like if first number is none, then just return the error response. Oops. Typo here with the following message. First number has not been set. Right? So once again, then let's comment out the first number and see whether we get what we expect. We run the script, and yeah, now when we run the tool, we get the error here, and then the 3 knowns. Similarly, with the second number, could happen the same, right? So let's also add a known default value for the second number and copy paste this block and update it to check on the second number. And the same thing goes for the tool name. If the tool name is not set, we set it to none automatically, and then we check that it's there. And now we have, for example, let's run this thing again. Yeah, you can see that even if the user forgets any of the values, it will get an error, right? But there's more things that can be wrong. Even if the user does not forget about everything, let's talk about, for example, the expected things, the expected data. So we are now expecting that the first number, second number to be integers or floats, because that's what we expect when we are operating with numbers for adding or multiplying. But what if the user sends a string? then some weird thing happens, right? So at least we should check that the first number, second numbers are actually numbers. So if not is instance, let's check that this first number is either an integer or a float. And if not, let's return first number is not a number. And the same thing for the second number. Second number. So now when we run the thing with a string, for example, we get the error that we have just coded. So what we have done so far is basically we have coded a very simple calculator that implements two different tools and handles errors whenever some value is missing or some number is not a number, and that's it, right? This, of course, is not specifically not very useful for a Mech tool, but it's a good exercise to understand the structure of Mech tools. So I think we can now move into. Yeah, I think we have a question. Let me check.
So it's not a question. So it's just to clarify, to add a little bit more clarification on what you have been representing so far. So it's to stress the importance that this run method on this Mech tool must satisfy the input and the output of the interface. So it must always output a tuple where the first element is the string, which should be like the response of what the tool has been doing. And the important thing is that it cannot raise any uncaught error or exception, because this will not work with the agent itself. So the agent expects that any error handling happens inside this one function. If there's any error state that occurs inside this function, it has to be processed, parsed, and sent as the response as a string of the first argument in this output.
Yeah, exactly. You are responsible for handling all errors. You can even, for safety, you can even wrap everything inside a try except. Maybe this is too much, but let's, for the sake of explaining this, you can wrap this inside a try except block, and then if anything happens, you can just send the error message to the user. That's what Jose has said is really important. Always remember, follow the function signature, both the input and the output, and also handle yourself the errors or exceptions inside the function. So now let's go with the second tool, which is a bit more interesting. For this, let me show you or talk about OpenRouter. So maybe some of you want to try to implement some LLM tool. And for this, usually, well, we need an API key. Whenever you implement a tool and it's integrated to the Mech, it's the responsibility of the dev, of the Mech operator, in this case, Valerie, to add all the required API keys to the deployment. But for local testing, as we are doing today, we need to have our own API keys. And not everyone has, for example, an OpenAI API key, because that requires a subscription. So for today, we will use OpenRouter. If you have an OpenAI key, that's okay. It also works with OpenRouter. Basically, OpenRouter is a unified interface for LLMs. Basically, it's an API that lets us send requests to multiple different LLMs from different companies. And the good part is that you can create a free account and create a free API key that will let you use some free LLMs. So if you haven't done so already, please go to OpenRouter, create a free account, and then go into your account, click on keys, and click here on create key. Once you click on create, you will be given a free API key. I think you have like a bunch of calls per month, but there's a lot of models that do not consume any credits. So basically, that's what we are going to do. Today, we are going to use a free model, which is Llama 3. So yeah, first, get your API key. Then, inside the repository, there's this sample.env file. This includes some environment variable, which is called OpenRouter API key. So whenever you have your key, please create a new file and call it like .env. Copy the environment variable, and here you set it to wherever you got it from OpenRouter, your key. All right. Once you have done so, and let me first add my own. 1 second. Let me remove this from the screen for 1 second. I am now pasting my key here. And now, let's open the script to run the tool. So similarly to how we had a script called run calculator request, I prepared another script called run prediction tool, which does basically the same with an extra step. This script will load your keys from the .env file. This is what happens here. And then similarly to how we did on the other tool, we just call the run function. And then we print the result. But first, let's have a look at the tool. So let's go to packages, Valory, customs, and prediction request. Once again, we have an empty or almost empty init.py file. We have a component YAML where we just updated the name, the author, the description, and there's no dependencies for this tool either. We also updated the entry point, but we kept the callable set to run. And then the important part, prediction request.py, the file that implements the tool. So let's have a look at what this tool does. First of all, I set something called the default model. Default model is the model that will be used in the case that the user does not set a custom model. This will be the Llama 3 8 billion parameters from Meta. You will see that some of the models from OpenRouter, you can search for these models on their website. The ones that end with :free are the ones that you can use for free. Then this tool is called prediction request. If you recall from yesterday, we were talking about prediction markets, where all these agents are making predictions and requests to the Mech to bet on these omen markets. So basically, this is about creating a tool which is able to predict somehow, even if it's in a very simple way, what are the chances of some event happening in the future. Normally, prediction tools make statistical analysis, use LLMs, or run all sort of crazy strategies. But today, we will be implementing a very simple tool that just makes a call to an LLM, asking to this LLM whether something will happen or not. Traditionally, we will have some yeah, as I said, statistic numbers there, like some chances, some what is the probability of something happening. But today we will just focusing on answering something like yes or no. So this event will happen or it won't happen at all. And for this, we need a prompt. We need a prompt to tell the LLM how we want it to behave. In this case, we have this prediction prompt that you are completely free to change and adapt to your needs, but it says something like this. You are an LLM inside a multi-agent system that takes in user questions about whether an event is likely to happen or not. Answers to those questions should only be Y for yes or N for no. You need to provide a yes/no answer based on your training data and only respond with the format below using curly brackets to encapsulate the variables within a JSON dictionary objects and not other text. So we are telling the LLM to only respond with a dictionary that includes the response set to either Y or M. And then we will add the user question called here user prompt. So this is like a template for the prompt. And once we have the user questions, we will replace this bracketed text here with the user prompt. You will remember this function from the previous tool. This is the error handler. Whenever we have an error, we will call this and we will just send the message back to the user. And now, once again, we define the run function that takes in some keyword arguments and returns 4 different things, for a total of 4 elements, a string with response and 3 other things that we will be setting to none today. The structure is similar to the other tool, but instead of having first number, second number, and tool, in this case, we are calling an LLM, right? So the first thing we need is a prompt. We also need a model, and then we also need an API key. So as we said before, we get the prompt from the keyword arguments, and if the prompt is not there, we set it to none. We check whether this prompt is none, and we return an error in that case. And whenever the prompt is okay, as I said before, we need to take the prediction prompt and replace this here with the actual question sent by the user. So we do prompt equals prediction prompt, and we replace the template with the prompt. This actually can be already changed to prompt. Now we have the prompt, we have checked that everything is okay, so we want now to get the model. But the good thing is that we already defined, if you remember at the top of the file, a default model. So in this case, I wanted to take a different approach. So let's say that if the user does not provide a model, I want the tool to use the default model, which is, once again, meta llama, llama 3, 8 billion parameters. All right? So no need for error checking here because we are automatically assigning the default model. The last thing we need is the API key. Remember, we are now testing locally, so we will pass our own API keys. But in the case of deployed tools, it is the Mech owner, the one that needs to set this key. So if you merge your tool into the Mech, you will need to request to Valerie, please, I need these API keys for my tool. Please set them on the Mech. So the open router API key is get from the keyword arguments. So this is the structure that the Mech tools usually expect, like a field called API keys that is a dictionary, and that includes like keys for open router or for OpenAI or whatever. In this case, we also set the default to none and check once again whether we have a key or not. If we don't have a key, we return an error. And now we already have the prompt, the model, and the key. So we are in the position now to already call the LLM. To call the LLM, this is a simple HTTP request. So this is how the Open Router API works. It expects some data, some dictionary, like this one, that defines the model. We set it as model, and then expects a list of messages. You can basically copy paste this as is, because it's the usual structure. Here we are saying, okay, this is the message from the user, and this is the content of the message, which is the prompt that we have calculated. So please run this model using this prompt. This is the data. We basically dump it into a JSON string because we are sending an HTTP request. So we have the data now, and we make a simple HTTP post request. So we call the request library.post. The URL is the same basically for every model. We need to set the headers, including the API key for authorization. If we don't set the key in the headers, this will fail and will complain about you not being logged in or not being allowed. So you set the authorization header to the better and set the API key. And then lastly, you pass the data. Once you get the response, you can retrieve the exact response from this object here. You get the response, you access the choices, you get the first element, message, content. This is, you don't need to do this if you want, but I did this because I just want this tool to return the message. But you could basically return the complete JSON object. And once again, we return the result and 3 non-objects. So I'm going to save my file. And here we go back to the script that calls this tool. So remember, we are loading the API keys from the .m file. We get it here from the environment, and then we just call the run function. I'm using the following prompt. Will autonomous agents play an important role on the economy someday? And then I also pass the keys in this format, as expected. And then we print the result. So let's run the thing. Python scripts run prediction tool. I run this, and there we go. Now we have run the tool. The tool has made an HTTP call to open router, specifying that it uses the default model, which is the free Llama trace model. And the result is a tuple that includes a string and 3 nonce, right? And the string, as we specified in the prompt, needs to follow JSON format so that we can basically load it using JSON.loads. And once we print the post-processed result, we get a dictionary that only contains a response field set to Y for yes. Remember that in the prompt, that's exactly what we asked the LLM to do. Only respond with the format below with curly brackets to encapsulate the variables, and only set the response. So yeah, this is how you run the tool, but sometimes you will get an error. And you just see it, right? Sometimes you run the tool and look at what happens. The result, try to access, this is what we are accessing at the bottom of the file, right? So here we're expecting to access something called choices. But what happens if the LLM fails for some reason or does not agree on the format? Then we will have an error, right? Because we are here taking for granted that there will be a choices field, a message field, that will be at least one element inside the choices, and there's content. So I will leave this to you to handle the potential failures that we can have whenever we access this. For now, just know that whenever you run this, sometimes it will fail, and sometimes it won't. Look, we have 3 failures in a row. The first one worked, but now it is failing, even if I have not changed anything, right? So yeah, I will leave this to you. and try to fix this and ensure that the user always gets a response back. There is one last thing that I want to comment today before we close the session for today, which is whenever you finish or change your tool, there's some important thing that you need to do. Let's say my tool is finished now and I want to submit it. We will see how to do this tomorrow, but be aware that inside the packages folder, there's this packages.json file that includes all the tools that are defined inside this repository. And each tool, look, here we have calculator request, and then we have prediction request, is linked to an IPFS hash. Every time you change the tool, you change, even if it's just a single comment, a single dot somewhere, you need to recalculate this hash. And the command to do that, it's autonomy packages log. When you run this, these hashes will be automatically calculated. Also, the hashes inside the other file, the customs.yaml file, you remember, sorry, the component.yaml file has some other hashes that also will be automatically recalculated when you run this command. So for example, now I have been changing something, right? This ends in RUE. I'm going to run this. And there you go. This has been updated to CRE. The same happened to this hash, and the same happened to these two hashes in the two different components of YAML. So every time you change your, or you have a new version of your tool, please run autonomy packages log, and the hashes will be calculated. It is very important to do this because tomorrow we will use this hash to mint our tool to the Olas protocol. We will see as well how to incorporate this tool into a pull request that can be merged into the Mech. And all the remaining part, and you have a complete minted deployed Mech tool that you have coded yourself, so you are eligible to get some dev rewards. So for tomorrow, what I recommend you to do is to try to run these two tools, then try to fix the second tool so the errors are always handled. You can also have a quick look to the Mech repo that we saw today and start thinking which tool you think would be interesting to code, because that will be completely on your own. Whenever you want to mint a tool, for tomorrow we will mint these tools that we have coded today, but if you have to mint your own, you will need to have some ideas about which tool you want to implement. Maybe it's a tool that calls the Google LLM, or maybe it's another thing that you find interesting. So yeah, for testing tomorrow, we will mint these simple examples, but you need to think about which libraries or which LLMs are interesting to have on the Mech. Maybe you can try to look at which other LLMs are in the OpenRouter website and change some things to have a unique tool that you can mint yourself. All right, so let's get cracking, and we can see you tomorrow with more. For today, do we have any questions on what we have seen today? I think we have some comments here, but yeah, I think Carol will make these videos available after the call. I think you should receive a mail with all the links and the video, right, Carol?
Yes, exactly. So you should already have received a follow-up mail from the session we had yesterday, and today you will receive another follow-up mail with these slides and the recording of this call. And I would also like to say that You are free to message anytime on Discord. We have that dev support channel that we can help you with whatever block or whatever you need. We will be there supporting you.
Exactly. Don't hesitate to ping me or on Discord, and yeah, I will be happy to help you guys. All right. Okay. Thank you everyone for coming, and see you tomorrow same time.
Thank you, David. Really nice session. Thank you, everyone. See you tomorrow.